Hi, in this lecture we are going to see hash functions. We have seen how we can support search, insert, and delete for arbitrary keys in space order of n and time just order of log n. There were a number of data structures that do that, and we have seen in detail how to do it with AA trees. Now, remember that if the keys are small integers, say integers in the range from 1 to t for a small t, then we can do it much more simply and efficiently. We can do it in time constant and space order of t. Okay, this was done just by direct addressing. We're going to place key I at the location I in an array, as we saw earlier. Can we have such fast times even for arbitrary keys? And an idea here is, let's make the keys small. And that's precisely what a hash function does. It's going to make the keys small so that we can have the same fast time as if the keys are small integers. Here is a picture of how a hash function works. We have u different keys, and we have a table just like before with t slots. And there is a function h which maps keys to slots. Okay? And critically, this function h has a parameter, the subscript a here. This choice for the parameter gives different functions, different arrows here. Okay? This picture here is for a specific value of a different value of a would have different arrows here. And the situation is that for every fixed choice for the parameter a, you can find keys that collide, whose images collide, as shown here. You can find these two keys which end up in the same slot. But the nice property of hash functions is that if you fix a priori n keys and then you choose the parameter a, then for most choices of the parameter a, there will be no collisions. Okay, so if you fix the keys first and then you choose the parameter a at random, then you have a nice mapping where the keys don't collide. So if you are in this lucky situation, then you can support insert, delete, and search for n keys using hash functions. Here is the setup. So the keys are coming from a large universe. Think of integers from 1 to u. The keys, in fact, the entire universe is being mapped by the hash function into a smaller set from 1 to t. Okay, so the hash function is mapping the universe to the elements from 1 to t. And the key property, again, that we want is that for each of our n keys, the values of h are different, so we have no collisions. In this case, then here is how you can support search, insert, and delete. We're going to keep an array S of t elements, and then search simply return the h search of x. First applies the hash function to x, is going to get a number from 1 to 10, and then it looks at the corresponding entry of the array S. If you want to insert an element x, again you compute the hash function of x, and then you set to 1 the corresponding entry of S, and delete is the same except the entry is set to 0. For a concrete example of parameters, you can think of having a number of keys which is 2 to the power 10, a very large universe of size 2 to the power 1000, and you can set a table of size 2 to the 20. We're going to see in a little bit that a table of this size will be able to guarantee that there are no collisions with high probability. Okay, again, can we have a fixed function h that always does this job? No. For a fixed function, you can find keys which give you collisions. No, if the function is fixed, then you can always find two keys x different from y that collide, okay? And so our function instead is going to be randomized. It's going to use randomness. The idea is that we want the function to behave like a random function, but another key property is that we want to be able to use this function. So we need a compact representation of the function so we can actually use it in an algorithm. And here is a specific construction of hash function. Okay, you're going to fix t to be a prime. Remember, t is the size of the image, okay? So you're going to map into an array from 1 to t. And for simplicity now, I'm going to think of t as being a prime, okay? And if you have a key, x, what I'm going to do, I'm going to write x in base t. Okay, I'm going to think of x as x1, x2, xm, okay, where each of these xi is one digit, okay, and the number of digits that you need is the log base t of u. Okay, so if you have numbers from 1 to u and you want to write them in base t, then you need log base t of u digits, okay, with remember it's the same thing as log base 2 of u divided by log base 2 of t. Okay, so the hash function itself is going to be specified by a seed element a, which again I'm going to think as being written in base t. So a will consist of m digits in base t, and here is the entire description of the hash function now. On an input x and the seed a, the hash function is going to do the following. Is going to sum, for i that goes from 1 to m, the product of the ith digit of the key and the ith digit of the seed a. Is going to sum all these products, and it's going to take the outputs, the final sum, modulo t. Okay, here is a concrete example. So we may pick t to be 97, and let's say our key is this number here. Okay. So if you write x in base t, then you have x1 is equal to 18, x2 is equal to 21, x3 is equal to 95. Okay, this can be verified. And then we have some values for the seed A, which are chosen at random. Let's say that our values are A1 is 45, A2 is 18, and A3 is 7. Okay, and then the value of the hash function on input x and seed A would be 18 times 45 plus 21 times 18 plus 95 times 7. Okay, this is a number. You're going to take this whole number modulo 97. That is, you take the remainder of this number when you divide it by 97, which happens to be 10 in this case. Okay, so this is a concrete construction of a hash function, and I want to mention a couple of variants. These are different constructions of hash functions. Okay. And for this, you should think that your keys are S bits and the output will be R bits. Okay, so instead of outputting from number from 1 to 2, you output r bits, which correspond to 2 to the power r numbers. Okay. So I want to mention a classic solution which you find in textbooks, in which the hash function on input x and seed a is going to first multiply a and x, take the product modulo p, and then everything modulo 2 to the r. Okay? And one problem with this is that this modular operation is somewhat slow, even if you pick some special prime numbers. An alternative solution which I want to mention to you, which is very popular in practice, is one which does not involve prime numbers, but just basic arithmetic. Okay? The way it works is that the seed b is a random odd number with s bits, and then the value of the hash function on seed b and input x is computed as follows. You just compute the integer product bx, okay, it's just the plain product of bx, and then you look at the binary representation of the product and you output the bits from the s minus r to s. Okay, so you just output r bits in the middle of this product. Okay, it's not so important exactly what this definition is, but an important feature of it is that it can be implemented very quickly. For example, in the programming language C, if you think of x as being an unsigned integer of 64 bits, okay, then the entire code for the computation of this hash function is this. It's b times x, and then you take right shift by u minus r bits. Okay, and this uses that some bits get truncated when you do this computation of 64 bits integers. So this is very fast. It's essentially just the time to compute one multiplication. It's much faster than this proposal, or even the one in the previous slide. It has somewhat weaker guarantees, but it can be shown that for many problems it suffices. Okay, let us now see how you analyze hash function. Okay, and let us go back to our proposal where the value of the hash function on seed A and input x, remember, was the sum over I of xi times ai, the product of the ith digit of the key and the ith digit of the seed, modulo t. Okay. So this function satisfies the 2-hash claim. Okay. So the 2-hash claim means that for every keys x and x prime which are different, then if you look at the probability over a uniform choice for the seed, okay, so you pick A uniformly at random, that the value of the hash function on x and x prime are equal, it's going to be small. It's going to be at most 1 over t. Okay. So this is the same thing as saying that on any two fixed inputs, the value of the function over a choice of a uniform A behaves just like a completely random function. Okay, so for now we are going to take this 2-hash claim as a given, and we are going to see how you can analyze the behavior on n keys as opposed to 2 keys. Okay, if you have n keys, then you need some kind of n-hash claim. Okay, so suppose that h is a hash function that maps the universe to the integers from 1 to t, and suppose that h satisfies the 2-hash claim. Okay, and then we make this claim here that if you have n keys and the output range is t, which is larger than 100 times n squared, then the probability that some 2 keys have the same hash is at most 1 over 100. Okay, So we have n keys, we map them to integers from 1 to 100 times n squared. Then the probability over A that any two keys have the same image is at most 1 over 100. And let us go through the proof because it uses some very important and basic machinery in probability theory. So what we want to bound again is the probability that there exist two different keys x and y whose hash values are the same. Okay? And the first thing that we do is what's called the union bound. Okay, we're gonna pull out this exist. Okay, this probability is always at the most the sum over pairs of keys x and y which are different of the probability over A that h of ax is equal to h of ay. Okay. Now this probability here we can bound using the 2-hash claim because it just talks about two keys. Okay, and we just saw that it's 1 over t by the 2-hash claim. And here on the left we are summing over every possible pair of keys. The number of such pairs is n squared. So overall we have n squared times 1 over t. Now we go back to our choice of t. T was at least 100 times n squared, so the overall bound is 1 over 100. Okay. Bottom line is that if you have n keys and you want to avoid collision with high probability, say 1 over 100 probability of error, then you just need to make your table size essentially quadratic in the number of keys. Let's say 100 times n squared. And a natural question is whether you can have no collisions with a space which is just linear in n as opposed to quadratic in n. And this is actually possible with a very nice idea which I'm going to present now. Okay, so if you give me n keys, then you can support a search in constant time and also using order of n space. And the idea is to perform a two-level hashing. So first we're going to hash to order of n elements. Okay, just like before. And because you only have order of n elements as opposed to order of n squared, you will have collisions. And then you're going to hash again. Okay? Then we're going to hash again using the previous method. So if the ith cell in the first level, okay, the ith slot of the table in the first level has some number c sub I elements, okay, then you're going to hash to ci square cells. Okay? Okay, and the amount of space that you're going to require is the sum of this ci square, the sum of all the ci square, and it is possible to bound this quantity and show that on average it will be order of n. Okay, let us recap with a comparison between trees and hashing. We have seen that both can support insert, search, and delete fast. So trees take logarithmic time, hashing can take constant time. So why would someone use trees as opposed to hashing? Okay, well, actually they're a bit different. So the nice thing about trees is that the trees maintain order. Okay, so you can also support other queries with trees. For example, you can support minimum. You can find the minimum element, or you can find the rank element. You can find how many elements are smaller than the element. And this thing is very important in many applications. Given an item, you may want to know what is how many items you have which are smaller than that. Okay. Also, you have a bit more control of what's going on. Okay, so it is possible to optimize trees for example, for disk operations. Some of those variants which I mentioned, like B trees, do that. Hash functions are faster. Okay, if you just want to search in certain delete, you can do it in constant time, but they destroy the order of your data. Okay, so once you hash, you don't know what's the minimum, you don't know the compute rank, and so on. And also, there is some small probability of error. So depending on your application, if you really have lots of data, you may start to have to worry about this probability of error, and then your tables become bigger and so on. Okay, that's it for now.